Hi, welcome to lesson number 17 on probability. And in this lesson, we study geometric distribution. If you remember, on lesson number 16, we studied Bernoulli distribution, and we said a Bernoulli trial is a trial which has two possible outcomes, either a success or a failure. And let's say the probability of success is equal to P, where P is between 0 and 1. Now, consider that you are conducting an experiment, which is a sequence of Bernoulli trials. So conduct a sequence of Bernoulli trials until the first success is observed. Until the first success. I want to mention that these Bernoulli trials are actually independent and identical. That is, the probability of success in each of the Bernoulli trials is constant. It doesn't change from trial to trial, and that is equal to P. Having said that, I can actually list, not a complete list, but a partial list of the sample space of this experiment. Now, my experiment ends when I observe a success. So if I observe a success in the first trial, that's the end of the experiment, because I have observed my first success. So one of the elements in the sample space is observing a success on the first trial, or failure on the first trial, followed by a success. That's another element of the sample space. Failure on the first, failure on the second, and a success on the third. That's again another element of the sample space. And so on. Now you see where I am going. Failure, 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 followed by success. Failure, 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 followed by success, and so on. Define the following random variable x, which I am going to call the geometric random variable, as the number of independent and identical Bernoulli trials needed to observe the first success. Needed for the first success. I can relate the value that this random variable takes to each of the points in the sample space. If you look at the first element of the sample space, S, that is the number of trials needed for the first success is 1 if you look at that. Therefore, x is equal to 1 if you observe a success on the first trial. Therefore, the probability that x is equal to 1 is equal to the probability of observing a success on the first trial. And the probability of observing a success in any trial is P. Therefore, the probability that x is equal to 1 is equal to P. The probability that x is equal to 2 corresponds to observing a failure on the first, followed by a success on the second trial. So that is failure on the first trial, and that is intersection, success on the second trial. Since the trials are independent, the probability of the intersection is equal to the product of the probabilities of each of those events. So the probability of failure on the first is 1 minus P, and the probability of success on the second is P. Therefore, P of x equals to 2 is P times 1 minus P. And I can relate this element in the sample space to x equal to 3. That is, the number of trials needed for the first success is 3 for that event. And the probability that x is equal to 3 is equal to observing a failure on the first, which has a probability of 1 minus p. And then a failure on the second, again with a probability of 1 minus p, multiplied by a success on the third, probability of p. And therefore that is equal to 1 minus p squared times p. Now, the probability that x takes any value little x is therefore equal to 1 minus p to the power of x minus 1 times p, where x takes a value of 1, 2, 3, 4, 5, 6, and so on. And therefore, that's the PMF of a geometric distribution. The PMF of a geometric distribution is given by 1 minus p to the power of x minus 1 times p. That is, if x is defined as the number of trials needed for the first success. Sometimes in exams or in some textbooks, they define geometric random variables slightly differently. And I could define the random variable y as the number of failures observed before the first success. Before the first success. If you look at the first element in the sample space, S, there are no failures observed before that success. Therefore, the corresponding value of y for that event in the sample space is 0, because there are no failures observed before that success. Therefore, the probability of y equals 0 is the same as the probability of x equals 1, which is p. If you look at the second element in the sample space, failure followed by success, the number of failures before the first success is equal to 1. And that corresponds to y equals 1. And that happens with probability of the event fs happening. And that is equal to 1 minus p times p. As you can see, y is always 1 less than x. That is, y is x minus 1. And I can write the PMF of y, p of y of little y, as 1 minus p to the power of y times p. Now, where y, the support of y, ranges from 0, 1, 2, and so on. So you have to be careful how the random variable is defined. If the random variable is defined as the number of trials needed for the first success, this is the PMF. If the random variable is defined as the number of failures before the first success, that is the PMF. In this case, if x is defined as the number of trials needed for the first success, the support starts from 1. In this case, the support starts from 0. So you have to be careful about that. Now, for the rest of this lesson, what I'm going to do is I'm actually going to use the definition x as the number of trials needed for the first success and find the CDF, f of x of little x, to be 1 minus p to the power of x. I'm also going to find the expected value of x, and that is 1 divided by p. I will then find the variance of x, which is going to be equal to 1 minus p divided by p squared. I will also find the MGF of x, mx of t, which would be p times e to the power of t divided by 1 minus p times e to the power of t. And the mode of the random variable x is going to be 1. I'm also going to find that. And finally, I am going to describe a property that we call memoryless property. Now, Let's find the CDF of a geometric random variable x. The CDF is, by definition, f of x of little x, which is the probability that x is less than or equal to little x. It's easier to find the probability of the complement of x is less than or equal to x. So what I'm going to do is, the CDF is equal to 1 minus the probability of the complement of that event, which is x is greater than little x. But since x is discrete, x is greater than little x is the same as 1 minus the probability that x is greater than or equal to x plus 1. Now, I can write this as 1 minus the sum k starting from x plus 1 to infinity of the probability that x takes a value of k, which again can be written as 1 minus. Let me actually expand this summation so you can see what's going on. 1 minus, when you plug in x plus 1 for k, you get 1 minus p to the power of x times p. When you plug in x plus 2 for x, you get 1 minus p to the power of x plus 1 times p. When you plug in x plus 3 for k, you get 1 minus p to the power of x plus 2 times p, plus, and so on, dot, dot, dot. What is common to all these expressions is that 1 minus p to the power of x and p are in every term. So I can take them out. 1 minus p to the power of 1 minus p to the power of x times p multiplied by, now when I take out 1 minus p to the power of x and p, I am left with 1 on the first term. The second term would have a 1 minus p. Third term would have 1 minus p to the power of 2, 1 minus p to the power of 3, and so on. So if you look at this term in square brackets, that can be written as 1 minus p to the power of x times p. That can be written as the sum, little k starting from 0 to infinity, of 1 minus p to the power of k. This summation that you have here is the sum of a geometric series. If you remember from your algebra, the geometric series is that if you have the sum k from 0 to infinity of r to the power of k, that is equal to 1 divided by 1 minus r if r is between 0 and 1. And of course, 1 minus p is between 0 and 1 here, because p is a probability. Now, everything that you have here in this summation is the same as this one here, except you have 1 minus p instead of r. So this summation can be written as 1 minus p to the power of x times p. Now, that summation is equal to 1 divided by 1 minus, the common ratio here is 1 minus p, which is 1 minus p. And now we are almost done. This is 1 minus p to the power of x times p. Now this denominator here simplifies. 1 minus 1 plus p is 1 over p. So I have 1 over p there. P cancels out with p. Therefore, I have my CDF. The CDF of a geometric random variable f of x is equal to 1 minus p to the power of x, for x equals 1, 2, 3, and so on. Okay, we have our CDF. And the CDF, which is the probability that x is less than or equal to x, is 1 minus 1 minus p to the power of x. What about the probability that x is greater than x? X greater than little x is the complement of x less than or equal to little x. So this probability is 1 minus that one. Therefore, it is 1 minus p to the power of x. And we have our CDF and probability that x is greater than x. This is sometimes called the survivor function. Okay? I'm going to split this lesson into two. So in the next part of this lesson, I am going to derive the moment generating function, the expectation, the variance, and show that a geometric distribution has memoryless property.